In this video, we're going to look at how we can form ethers and cleave ethers, so you should have familiarized yourself through the text through some of these processes. In this example right here, we're going to start with an end product ether and figure out how we got there. And the hint that I'm going to give you is we're going to use Williamson ether synthesis. Let's start by looking at the product. We need to figure out who the players in this reaction are. If we remember how Williamson ether synthesis works, we know that we start with an alcohol, we deprotonate the alcohol, and then it attacks an alkyl halide. Let's start by identifying what our alcohol could be. Now here there are two options, and we will need to decide which one we're going to start with. We can either have this be the precursor to the alcohol, and anything outside, right to the right of this oxygen, would be the hydrogen, or it could be this. So the question is, how do we choose? You should remember that one of the important parts of Williamson ether synthesis is that it works by an SN2 mechanism, and I'll write that here, where the deprotonated alcohol acts as a nucleophile to attack the alkyl halide, which means that if we start with option 1, with this, the alcohol that I identified right here, then our alkyl halide would look like this. And I'll just use iodine. But if it works in a SN2 mechanism, anything I draw to attack through a backside attack is going to be very sterically hindered, which wouldn't be a great option to use. So let's consider if we used option 2 on the right, the alcohol identified there, which would mean that our alkyl halide would look somewhat like this. And the attack would be coming in the back here, which would work. That would be that's a primary alkyl halide. So now we've identified the alcohol we're going to start with. So I'll go ahead and draw that out. And we know that we need to deprotonate it, so typically a good one to use is sodium hydride. So the hydride will come in and abstract the proton. I'll just draw an arrow back on the oxygen to show that the electrons in the bond are going back onto the oxygen. Now we've created our tert butoxide, this alkoxide, right here, the negative charge on the oxygen. And now we're going to want to add our alkyl halide, and we decided earlier that that would be this. Just the iodine. I've always used iodine. And our nucleophile is going to come in and attack. So nucleophilic attack, loss of a leaving group, and that will get us our end product. So here we applied the concepts of what Williamson ether synthesis was, the fact that it works by an SN2 mechanism to decide our starting material, and that helped us decide what we're going to add to the reaction. In this case, what was our alkyl halide. Now we're going to take the product that we got in the previous slide, and we're going to cleave it into a selection of alkyl halides and some water through a process called acidic cleavage. So you should be familiar with this process. The main idea here being that we want to liberate these carbons from the oxygen in the middle. And as you might expect, that oxygen is going to become part of the water. The name acidic cleavage implies that we're going to be using acid, and in terms of what we're actually going to put in the reaction, we'll use excess acid, in this case hydrobromic acid, and we'll add some heat as well. Since we're wanting to create alkyl halides, the question should be, how are we going to liberate a group of carbons such as this one from the oxygen? If we considered trying to have this act as a leaving group, the way it is now, it would be a horrible leaving group because we get an alkoxide. And as from what you've learned in earlier chapters in the book, that's a pretty bad leaving group. It's like hydroxide as a leaving group. But you should remember that we can protonate this to make it a great leaving group, as great as water is a leaving group, since water and alcohol have very similar properties. Since we have acid in the solution, that's how we're going to start. I'll go ahead and draw a molecule of the hydrobromic acid. We'll have a lone pair come in and take the hydrogen off, and that will get us this. Take a minute to draw. But we're going to have our protonated ether, positive formal charge on the oxygen. Always be reevaluating that, what's changing over the reaction. And let's not forget to draw the ion over here. So now we should notice that we actually have something that could act as a great leaving group because we'll be kicking off an alcohol. So we could have our nucleophile, in this case the bromide, and that will come in and it can attack here through an SN2 process and thus kick off the alcohol, which would get us this. We have one of our alkyl halides plus our alcohol that we created. So now, from what you expect, if we're trying to liberate the rest of these carbon atoms, we're just going to repeat the process again, and I'll switch colors to highlight that fact. So, what's the first step? We need to protonate the alcohol. So we know we have acid in the solution, that excess amount, and we're going to have a lone pair from the oxygen, come on, abstract a proton, and then we'll have the electrons between the hydrogen and the bromine atom move on to the bromine, which will form our ion. And that will get us this. We'll have the oxygen with the positive charge attached to these carbons. We have our bromine that's still in solution. And then, like we saw before, we're going to have an SN2 attack here, thus kicking off the water. Which, if you go back here, that will give us our alkyl halide plus water. So now we have our final products of the reaction, the two alkyl halides and water. But one thing that should have you wondering is something over here, where we got an SN2 mechanism that attacked a tertiary carbon. Steric hindrance tells us that shouldn't happen too often, but turn this into a thought question and consider what might make this possible in terms of this bromine atom coming in and attacking a sterically hindered position like this. Before we wrap up this video, I want to propose a question that you can do on your own. Here I've given you an alkene and we've actually made an ether from starting with that. Now you should know that here it's going to be pretty difficult just to start by doing a simple Williamson ether synthesis, but consider another reaction that you've learned before in some of the earlier chapters, even in Organic Chemistry 1, that has allowed us to add an oxygen atom or oxygen group to an alkane. And I'll let you try to work that one out on your own, and you can find some guidance in the book as well.